Differentiation, lesson 9, is all about how we sketch the graph of a derived function. We've already known how to sketch graphs of functions, y equals 3x squared plus 2x plus 7, all right? Or if we say f of x equals, we still can plot those points, x coordinates and y coordinates. But what if we've given a graph and we say, what's the graph of the derivative of that? Here's how it works. Normally, it's fairly straightforward, 2 or 3 marks in the exam. The only crucial thing you really need to remember is we know that when a line is going down from left to right, when a graph is doing that, then we say the graph is decreasing, the gradient must be negative. To put it another way, f dash x is less than 0. We know when a graph is horizontal, even if it's just for a moment, like at the stationary point, at that point, the gradient is 0. And of course, if the graph is going up from left to right, if the graph is increasing, then we say the gradient is positive. And if we can remember these 3 things, then that is all the new knowledge we need, and it's old knowledge, of course, to do this question. Here's an example. Bottom of page 13 in your notes. I always do a derived graph directly in line with the original graph. So here's a graph which is a parabola. So my f of x be something like 3x squared minus 2x plus 7 or something like that. And it's a stationary point here. I've not even got identified the coordinate, either the x coordinate or the y coordinate of this stationary point. I don't know any coordinates on this graph at all. I just have the shape. On my derived graph, well, on here, instead of f of x, we have f dashed x. So it's a measure of the gradients of this graph down here. Start with the stationary points. I know at this point the gradient is 0. So exactly in line coming down here, if this graph, if my y coordinate here is measuring what's the gradient up here, the gradient here is 0. So on here my y coordinate is 0. What do I know about to the left of my stationary point here? The graph is coming down the whole way, so I know that here the gradient is negative. So on my graph below, make my y coordinate negative. So I'll put a little point in here. To the right of my stationary point, the graph is going up all the time, so the gradient is positive. There's different values, but it's always positive. So to the right of here, my y coordinate must be above the x-axis. It must be a positive value. And then draw a line through. Normally say do a smooth curve. In this case, I've done a straight line. Why? Because we know that if we have something like f of x equals x squared, whether there's something else after that, like f of x squared plus 3x plus 2 or whatever, when I differentiate x squared, I get 2x. My powers go down 1 when I differentiate. We said that right at the beginning. When you differentiate, take 1 off the power. So if it's x squared, no matter what the other numbers are, the other coefficients and other terms, if the highest power here is x squared, then my derived graph becomes x to the power of 1, something like 3x minus 6 or something, which is a straight line, mx plus c. That may sound a little confusing, but let me show you how it works actually more easily on a more complicated one. Example number 2. Here's a graph with 2 stationary points. Again, I don't know where it cuts the y-axis. I don't know the coordinates of the stationary points or anything, but I do see that I've got 2 stationary points here. This would actually be a graph. 2 stationary points normally means it's something to do with x cubed. X cubed is my highest power. Again, underneath, exactly in line, I'll do my sketch of my derived graph. So here again, f dashed x. The crucial points here are where the gradient is 0, my stationary points. So exactly in line with these, whatever the x coordinate is, even if I don't know it, the gradient is 0 here. So on this graph, it must cross here. That's my 0 for my y coordinate. Likewise here, another stationary point. So if I come down vertically to my graph underneath, whatever this x-coordinate is, same x-coordinate down here, but my gradient is 0, so I'll mark this as 0. Now let's just look what's happening either side of the stationary points. On this one, before this first stationary point, to the left of it, my gradient is positive. It's coming up and up. Different values, but it's always positive. So I know in here, my curve must be, the y-coordinate must be positive. My y-coordinate is the same as my f dashed x. It's the same as my gradient. Gradient is positive here. Make sure my curve on here is positive. So I'm just going to put a dot anywhere that's above the y-axis, just to show it's going to be a positive. What's happening between the first stationary point and my second stationary point? My graph is negative, or my gradient is negative. The graph is going down. Okay, on here, I'll mark a gradient. My gradient graph is being negative. My y-coordinate is going to be below the x-axis. That's a negative value. Positive value, 0. Negative value, 0 again for the stationary point. To the right, what can I see here? My gradient is positive all the time. So on here, I know my curve must be somewhere above the x-axis, where my y-coordinates are positive. And then you simply draw a smooth curve, no jaggy lines, right? No extra little points of inflection or anything, just a smooth curve going through the points I have here. And if I need to adjust one up or down, so long as this, to the left of here, I'm above the x-axis, because that's all positive values, below between these 2 points, and above again. So I'm just going to do a curve something like that. Make sure it's not jaggy at the bottom, it's not mountains, it's smooth rolling hills. And that's my graph f-x. That's my derived graph. And again, as I said, if you happen to know this 2 stationary points is normally a cubic, highest power is x cubed. Then when we differentiate x cubed, we get something x squared, and that's a parabola with 1 stationary point. So something like that. Crucial point thing is that the stationary points are in line with 0 on here, because on stationary points, the gradient is 0. Final example, over on page 14. Add this. A little bit different this time, because here's a graph and we've got some coordinates in here. Crossing the y-axis at the point 0,8. There is a point of inflection when x is 1, but we don't know the y-coordinate. It may be 7, but it may be 6. It could be something else. So we'll just know that that's the x-coordinate here. Cuts the x-axis when x equals 2. A minimum turning point at x equals 3. Cuts the x-axis again when x equals 4. And a maximum turning point when x equals 5. So add that in diagram to your notes, please, smoothly as you can. And the question just says, sketch the derived function. We don't know the values of the gradients here, but we do know if they're positive or negative or 0. So on the graph underneath, my f-x graph, same scale as the one above, keeping everything in line. Let's mark where the gradient is 0. The gradient is 0 when x equals 1. So down here, that will be, this point must be on our derived graph. The gradient is 0, not here at 2, that's because the gradient is very negative here. The gradient is 0 here at this minimum turning point when x is 3. So I know these 2 points must be on my graph. And there's a final stationary point here. When x is 5, the gradient is 0. So down here, so these 3 points must feature on the curve that I'm going to draw down here for my derived graph. What else do I know? To the left of this stationary point, the gradient is negative. So I'll just mark a point below the x-axis because my y value is negative. Between 1 and 3, not between 1 and 2, but between 1 and 3, the gradient is negative all the way. So between 1 and 3, I'll have a negative gradient. I'll just mark a point again below. No scale on the y-axis here, but I do know it's negative, so it's below here. Between 3 and 5, my gradient is positive. So that will be up here somewhere. Positive point. And last but not least, to the right of my third stationary point, to the right of 5, my gradient is always negative. So to the right of 5, my gradient is negative. In drawing the derived graph, what's the significance of this 8 here? Absolutely no significance whatsoever. What's the significance that it cuts the x-axis at 2, 0, and again at 4, 0? When I come to draw the derived graph, what effect does these coordinates have on the gradient? Absolutely none. So the fact that it crosses here, 2, 0, 4, 0, that it crosses here at 0, 8, none of that is significant when I'm doing a sketch of the gradients, because that's all the derived graph is, a sketch of the gradients. So I'm just interested when the gradient is 0, and then what's happening with the gradients round about the zeros. Negative, negative again, positive here, negative in the end. I mark the zeros, I mark negative, just a negative value, no particular value except it's below, and above, and then below. And finally, draw a smooth curve through them all. Nothing jaggy again, so I'm just going to do there, make it nice and smooth, because I know I have to come down again here. Then I need to go up again, so I'm turning. What's happening here? I'm going up past that, so I'm just going to go through here at 3. I know once I've gone positive, I've got to come down, so again, a smooth line coming down. And then at this point, I keep coming down because this line is below, so I'm going to do that. And I'm not going exactly through that, but the point is it must be below, so it doesn't have to go exactly through that cross. I don't need to sort of force the line over there, so long as I'm going from below to 0, below, above, and below. That is a perfectly good graph for f dash to x, my derived graph from this curve here. That's basically it done. There's a little footnote here just pointing out something we've already been talking about. If a graph is a quadratic, in other words the highest power is x squared, then our derived graph is a line because it's just x to the power of 1. If f of x is a cubic, x cubed plus so many x squared plus x plus 1, the highest power is x cubed, our derived graph will be x squared, which will be a parabola. And that continues, etc. Right, if it's what's called a quartic, highest power is x to the 4, then my derived graph will be a cubic, something x cubed, because that's what happens when we differentiate. And that is it in a nutshell.